So, good day. The title of my lecture is the GW method, a common approximation and practical implementation. What we want to tell you with this lecture is how to pass from the theory that we have seen in the previous lecture to practical implementation in the Yambo code through all the approximation that we will use to arrive to our final results. As we have seen again in the previous lectures, we are interested in calculating quantities that we can then measure experimentally, as for instance, photoemission experiment. In photoemission experiment, we have seen we measure the kinetic energy of an upcoming electron ejected from a light pulse, and this energy will be then will provide us information on difference of energy between a system with an electron and a system with n-1 electron. So let's start from the DFT, the workhorse for electronic structure calculation. We know the Kohn-Sham, the well-known Kohn-Sham equation. These are the equation of non-interactive systems with an effective exchange correlation potential. This moderate, it has moderate computational cost, predict ground state geometries, electronic structure with a great accuracy. And what about, for instance, the gap of materials? Here it is a famous plot. We have different semiconductor insulators. And as you can see, these are calculations done with a local density approximation compared with experiment, and the agreement is very pure. The problem is not the local density approximation. So again, let's look again what is exactly the gap as measured from a direct and inverse photoemission experiments. Is the difference between electrode affinity ionization potential, and by their definition, you can recognize that the ejection or removal of an electron is always a many-body process. So the question is, we can calculate the gap directly using a total energy from DFT. The answer is yes and not at the same time. Here, if we look at the gap as a difference of eigenvalues, we realize that it's not the right definition of the gap. Here, doing some algebra from the total energy of a DFT calculation, we can see there are many terms missing. But if we do calculate using energy difference, for instance, here is a set of molecules, we see that we can find reasonable results. But the problem is we don't know how to consider n+1 or n-1 electron system for a periodic solids. So we need a theory that can link exactly the n-particle system and n+ or -1 particle system. This is a many-body perturbation theory, and the quantity we want to look at is the green function. The green function contains the exact right excitation energy beside other quantities, observable size excitation lifetime, ground state density, in general expectation values of one particle operator, including total energy. So we have seen already how it is defined, the green function. And the green function, by Fourier transform, we can recognize that has the poles are the true many particle excitation energy we are looking at. So how to obtain this green function practically? Now this is the problem we want to look at. Here it comes perturbation theory. Let's start from something that is known, and we want to evaluate something that is not known, hoping the difference is small. So let's name G0 the green function of a non-interacting electron Hamiltonians. We consider an interaction, and let's define the difference between these two quantities, the self-energy of our problem. So the equation we have seen before can be cast in this way. let's suppose that we note the G naught, the green function of the mean field systems, and we can arrive to this equation that is the quasi-particle equation. If you inspect this equation, there are similarities with respect to the Kohn-Sham equation, but difference, we have the self-energy instead of the local potential xg. The self-energy is not Hermitian, is non-local, is frequency dependent. And while the exchange correlation potential is the part, is the potential of a fictitious Kohn-Sham system, now the self-energy is the potential felt by an added removed electron from or to our system. Besides that, the eigenvalues will be complex quantities. Okay, so how to obtain, in order to build our equation, now we want to see how to obtain the self-energy. This, the answer is given by the Hedin equation we have seen before. We start considering the green function of the non-interacting system, so the self-energy will be 0. And here, neglecting the vertex, we arrive to our definition of the self-energy, that it is indeed GW. So here an important remark, note that the vertex has been neglected, so this is an approximation. And here we insert another very common approximation in the calculation. We consider the non-interacting green function, G naught. So now we have our quasi-particle equation. We know how it is defined, the self-energy. We consider the green function of the non-interacting system, and we arrive to our equation now that G naught W for our self-energy. Now W provides up the polarization and screening. It is a Dyson equation and contained in the Hedin equation. And now the polarization with our choice that G equal G naught is defined as G naught G naught. So the starting point is here. We solve the independent particle calculation, Kohn-Sham system, for instance, local density approximation. And we can build our polarization made of non-interacting electron and holes in this way that I show here below. So the screening, once we have the polarization, it is what is called the random phase approximation. We consider a classical Hart interaction between an additional charge in the system and the created polarization charge. This is the very famous random phase approximation. And when we look at the Dyson equation, our Skrivet interaction will contain all the bubble of the polarization, this called bubble approximation, and the potential, the Coulomb potential at all the orders. So now we have our self-energy at the so-called G naught W naught level. It is a common practice to separate in exchange and correlation part. The exchange part, the integral in frequency can be done analytically, and we arrive exactly to a Hartree-Fock exchange term. And while the correlation term had to be computed numerically, the integral of a frequency and the most time-consuming part of our calculation. Different implementation exist in the literature in various code. Yambo is a reciprocal space and frequency domain code for the GW, as for instance other code as Abinit and VAST, but here some reference, it exists many other implementations of the GW calculation. Here, don't be scared, it's just writing the two parts, the two components of the self-energy in a plane wave basis set. And we start to see that in order to compute this quantity, we need to do an integration over the Brillouin zone, so k-point sampling convergences. We have some over states, some over unoccupied states, and the most painful part, an integration in the energy domain. Here, just very quickly, this is something you will see in the afternoon in the hands-on. These are exactly the variable that we have to check in input to converge. So in the case of the exchange part of the energy, the cutoff in plane wave, and the k-points grid. For the correlation parts, we have also the unoccupied states, and we have here the epsilon minus 1, that is the block, it is the electric matrix, the electric matrix, and we have to converge his dimension, the block size of the dimension. Now, the frequency dependent part, what it is usually done, but not always, is the so-called plasmon pole approximation. We assume that the frequency dependence of the dielectric matrix can be modeled with just one pole. This is the plasmon pole approximation. We have now an analytical expression for the frequency dependence. The integral can be solved analytically. This simplifies a lot the problem, but consider the different recipes exist in the literature to evaluate the poles and residues of the electric matrix, and these give also to different results in many cases. Here I compare for some typical insulators, silicon, carbon, zinc oxide, the full frequency expressions of our dielectric matrix with respect to different different flavor of plasmon pole. In many cases, here the results of the gap, considering for several materials, considering different recipes, while for silicon and diamond, we have very similar results. There are cases, as for instance, the zinc oxide, where the discrepancy is very huge. So it's important to check also the model of the plasmon pole you are assuming, but note the plasmon pole approximation becomes questionable when the frequency dependence for a material where it is not possible to approximate with a single pole, it's questionable. For instance, interfaces of the electrons in copper, just to few examples. And in this case, fuel integration is needed. So now we know how to build our self-energy. We know also how to integrate it in frequency. In order to solve the quasiparticle equation, here it comes another approximations that our amplitude of the quasiparticle approximated by Kohn-Sham states. Once we have done that, we can, for instance, solve our nonlinear equations by expanding at first order around the Kohn-Sham energy. So here, to recap, the workflow of our calculation will start always for a Kohn-Sham DFT calculation. You choose your exchange correlation potential. From the eigenstate and eigenfunction, you can build your non-interacting green function, your P0, your polarization. Then you can, with the polarization, you can build your screened interaction, also frequency dependent, for instance, via plasmon pole approximation, and then solve the quasiparticle equation and obtain the quasiparticle energy. So now, how good are these G0 and W0 approximation? Here some results are shown before. You can see that now we have a quite good, reasonable agreement, and a good and a huge improvement with respect to the results obtained in density and functional theory. This is not the end of the story, not here for diamond. This perfect agreement is, agreement is perfect, but for a wrong reason. We can maybe discuss later the reason why it happens. So we have solved our GW equation. We have quasi-particle calculation. We can think about also to calculate absorption. The answer usually is not. Here it is for a simple system silicon. I compare the absorption spectrum with the experiment, DFT, GW, the experimental feature are not catch at all. So something is missing. There's something you will see in the next days of the school. So some conclusive remarks. Many virtues of the GW approximation is a parametric field method, and that provides in most of the case accurate results. It is the starting point also for calculation of spectroscopy, but other ingredients are needed. And today is feasible for medium-sized system. The algorithm is suitable for HP computation, particularly for GPU cards. But if your results don't match the experiments, don't worry. So check always carefully your convergences parameter. It is very, very important. And even at G0 W naught, which is the simplest approximation, here I just put several parameters that you have to carefully check before having a meaningful results. Even if you converge everything, do not forget that this is a GW, it is an approximation for the self-energy. Vertex effects are being neglected. Many approximation enters in the practical calculation that I showed before. Here are summarized, plus one-pole model, RPA level for the screening, and you can observe also an important dependence from the DFT starting point you use to build your green function and your screening. So here I conclude. I leave here some reference, the seminal paper of the Edin and Lundquist, some review, including some recent reviews about the method. These are the two papers with the implementation in the Yambo code. And I thank you for your attention.